Hello everyone, in this video we will be discussing on the BJT operation. This is a self-learning topic number 2 under the course of digital design. We're learning the second self-learning topic as BJT operation. And this is a very important topic because the BJT is used for all the different logic family gates. That is for all the bipolar devices, you would be having a BJT. So you should know a few of the basics of the BJT operation. That is very, very important. What is an BJT? BJT stands for bipolar junction transistor. The first definition you can say is an bipolar junction transistor. So why it is called as bipolar is that you would be having two bi indicates 2. So you will be having a combination of both these one minority carriers and majority carriers both to taken into consideration. That's the reason it is called as bipolar junction transistor. There will be a formation of two junctions over there. One is between the P and N and N and P. There will be two junctions over there. That's the reason it is called as bipolar. So coming to the over here, BJT consists of three regions. One is an collector, the other one is base, and the third one is emitter. Collector, base, and emitter. These are the three regions available in an BJT. So two types of BJT are available. One is an NPN, the other one is PNP. So both are there would be two regions over there. NPN region and NPN transistor and PNP transistor. So three terminals, base, emitter, collector, and two types of BJT, NPN and PNP. So when you go for obviously transistor is a semiconductor device. When we go for a semiconductor device, there would be two. When you go for a semiconductor device of NPN transistor, there would be two N regions, okay, and one P-type layer. And for PNP transistor, you would be having one N-type layer and two P-type layers would be there. So here, the formation would be such a way that you would be having a sandwich of in the between of sandwich, you would be having a base. Other side, you would be having emitter and collector. This side and this side, in the center, you would be having the base. So three terminals would be taken into consideration like this. So bipolar devices, and one more thing you can have it of a very important point is that when you go for NPN or PNP, both emitter and collector are having the same type of doping, and base would be having a different opposite doping when compared to here. When you say material would be of different type other than the emitter and collector. So see, in every PN junction diode, we'll be having two types of biasing. One is a forward bias, the other one is reverse bias. So to say in forward bias, we will say when it is the transistor is connected in forward bias, we will say that it is conducting, and when the transistor is said to be in reverse bias, it is not conducting. And there would be different biasing techniques which are used over there in BJT. Okay. Okay. So coming to the first one, when you check out the circuit symbols of BJT, the first one is a PNP. In the PNP, you can see the middle layer, which is a very thin layer when compared to the other two layers. It has been located in the middle, which is called as a base layer. And the other two layers are emitter and collector. Similarly, for the NPN also, the middle layer is the base layer, which is a thin layer. The other two layers are the emitter and collectors, which are made up of the same type of semiconductor material, while the base is of other type of material which is there. And the circuit symbols have been shown over here. This is NPN and PNP. The more important thing over here is that in this circuit symbol, you can see this arrow. Okay, the direction of the arrow, how the direction of the arrow is there, and you need to circle out the transistor or this one. So each of the transistor will have three different currents. One is a base current, the other one is collector current, and the third one is the emitter current. And it is been given such a way that the sum of the currents, mean to say the current IE is the sum of these two currents. IC and IB are added to form I current, emitter current. Okay, so that is the current equations which is been given for an transistor currents equation. So wherever you find an arrow is drawn onto the emitter, where it is moving inward and outward, this arrow will indicate the NPN and PNP transistor. Now, one more thing, more precisely we can say, the analogy of a transistor is nothing but, I think you have heard about back-to-back diodes. When you connect two back-to-back diodes, then it is said to be a transistor. So, how the diodes should be connected when you are having an PNP and NPN, it has been shown in the figure. So, you can see these two diagrams. Now, so here, when the transistor is said to be a forward bias, when it is said to be reverse bias. So what we'll do is that when the emitter, I mean to say positive end of the terminal is being connected to the positive end of the power supply, it is said to be a forward bias. And positive end of the power supply is being connected to negative end of the power supply, then it is called as a reverse bias. So when you go for a basic operation of the transistor, the first one is that when you connect this one, what happens is that these positive ions would be repelling this one. Okay. So here what happens is that the N-type region, which is a little bit larger previously, it goes on shrinking, and these protons will move away from and they would be such a way that it would be traveling from positive end, and it would be moving over there, and there a majority carriers would be flowing from one direction to other direction, and the transistor conducts. Whereas when you go for reverse bias, the transistor, what happens is that this depletion region, we say there is a depletion region, or the region between the two N-type base region extends over here. The positive ions are being attracted to the negative power supply, and the region is been extended. As you see in this diagram, the previous diagram, there is no, the region is getting thinner up, and here a additional layer is been added. In this one, this layer is been added additionally. So this is the reverse bias. So the same thing in my this would be the flow of current, which would be there, majority carriers and minority carriers, and the transistor would be working. So around here, you need to remember that when you apply a certain voltage, then only there would be you need to remember that there would be a certain cut-in voltage for the transistor, and saturation voltage of the transistor, and base emitter voltage would be what, and what is the saturation voltage, what is the cut-in voltage, all this one. So the first thing is that the cut-in voltage for the transistor is 0.65 to 0.7, where the transistor starts conducting, And if you are applying a voltage more than 1.2 or something, or nearly about 1 volts, automatically the transistor starts turning, and at one time it would be fully conducting and moves into the saturation. And similarly, the base emitter voltage would be equal to what? 27 volts. Like the diode conduction voltage, it would be the base emitter voltage would be there. Then it would be when the transistor is conducting, it is you would be having base emitter voltage equal to 0.7 voltage. And the saturation voltage, when the transistor is fully conducting, the saturation voltage VCE saturation would be equal to 0.2 volts. Voltage across uh, emitter and collector would be, when it is in saturation, it would be 0.2 volts. That should be remembered. This is very important for your understanding. Thank you for watching this video. So in the next videos, we will be discussing the classroom discussion. Thank you.